Today I will introduce a box model for analyze the water balance of Guantao shallow aquifer. This is the content of my presentation. First, I will introduce the background. What is a box model? What problem it can solve? And also the study area of the Guantao County. Then I will introduce how to set up the box model and what application it can be done and the outscaling of this box model. We also developed the box model in Excel. I will introduce it in the final part of my presentation. So first, what is a box model? A box model takes the study object as a whole. It obeys the law of conservation of a mass. In the hydrology studies, usually we take the study object as a water tank. We look at the water balance of this water tank. So the change of storage of this water tank equals to the inflow minus outflow. So a box model can be seen as a lumped conceptual model that is with comparison to the usually used distributed groundwater models. Because it takes the object as a whole, it ignores the internal variables of the system. It also neglects the special distribution of the variables in this system. But it allows us to do the analysis on the overall level. It has a very simple structures and easy to understand. So it is very helpful to identify the unknown variables. It can provide basis for the numerical distributed groundwater model. So what problem can be solved by a box water balance model? It can be applied in many areas. For example, it can be used to assess the reservoir operations. Also in hydrology, the lumped water balance model can be used to analyze the basin rainfall runoff generation to understand the hydrological components. A box model of water balance can also be used to assess the sustainability of aquifer use for agricultural use. This is similar with the study I am introducing today. So our study area is still Guantao County. The audience already have an idea about Guantao County. It locates in the alluvial plain zone. Most of the irrigation water comes from the shallow unconfined aquifer. That is why we focus on the shallow aquifer. There is also some irrigation water comes from deep confined aquifer and some from surface water in the recent decades. There is no water metering at the irrigation wells, but all the electricity are metered. This is the basis of groundwater pumping monitoring. This is the research goals. We would like to set up a water balance model of the shallow aquifer and would like to develop a simple model for groundwater level simulation, which can be an alternative option to substitute the distributed groundwater models. And the results of this simple model can serve as a basis for the following distributed numerical models. In one word, we would like to supply a simplified and the transferable method for decision support. This is the sketch of Guantao aquifers. The shallow aquifers thickness is around 90 meters, and there is about 100 meters aquitard in between of the shallow aquifer and the deep aquifer. We focus on this shallow aquifer. To look at the water balance of this shallow aquifer box, we also first need to look at the exchange between this box and the other two boxes, the deep aquifer and the vital zone. What we know for sure is the rainfall and the irrigation backflow recharges the shallow aquifer through the vital zone. And the discharge is abstraction for irrigation, this red arrow. There are some variables can be ignored because the depth of groundwater in the shallow aquifer is very low, about 20 meters. The phreatic evapotranspiration can be ignored. Also, the exfiltration to the rivers and other surface water bodies can be ignored. Compared to the vertical exchange, the lateral exchange of flux can be ignored, and also the exchange between the shallow aquifer and the deep aquifer can be ignored. Also, since groundwater abstraction of the shallow aquifer is mainly for agricultural use, for irrigation, the other use of the shallow water can be also ignored. So let's look at in detail of this shallow aquifer box. First is the discharge. There is only one discharge, the abstraction for irrigation. The recharge, first there is a rainfall infiltration, and second there is a irrigation backflow. The irrigation water comes from a shallow aquifer, deep aquifer, and surface water. There is also seepage from the river and from the canal in the middle of the county. The change in storage of the shallow aquifer can be calculated as the products of change in water level, specific yield, and the area. So we can write the equation of water balance of the shallow aquifer as this. The water balance is calculated at yearly steps in our study. This is the structure of this box model. It is quite simple. The most important thing is how to estimate each of the variables in this water balance equation. I will introduce it one by one. First, let's look at the discharge, the groundwater abstraction for irrigation. Usually in water balance analysis, groundwater abstraction is an unknown. This is because the groundwater abstraction is very difficult to monitor. The common method is water meters, but it is difficult to maintain, and there are a huge number of small-scale wells in the North China Plain. Direct water metering is not feasible. The other method is to estimate groundwater use or the irrigation water use by the product of water use per unit area and the total irrigation area. It can be less accurate due to the estimation of water use per unit area. In our project, we developed two tools. One is irrigation calculator, which will be introduced tomorrow, and also the crop mapping to estimate the irrigation area from remote sensing, which has been introduced yesterday. By these tools, we can estimate the water demand of the crop, but it is still there is a still deviation from the actual water applied in the field. So can we find a method that is easy to maintain and also provide accuracy? Yes, this is the monitoring method using electric energy as proxy, which has been explained in detail from the yesterday's presentation. I will still introduce it briefly. We use electricity to water conversion factor to convert electricity to water volume. It has many advantages because the electricity metering system is well maintained by the electricity department. So the cost of this monitoring method is very low. We only need to do the pumping tests to determine the conversion factor. And the electricity records is very objective data. It can be used to reconstruct historical groundwater pumping. And this method is financial, cheap, and easy to maintain. It is suitable for the whole North China Plain. To get you some memories from yesterday, I still briefly introduce how we determine the conversion factor. We do the pumping test to get the conversion factor at the water level, at the present water level. To determine the conversion factor in history, when the water level is not so low, we use the equation derived from the conservation of energy. It is a function of efficiency and pump lift, which composed of the depth of groundwater level and the additional drawdown and head losses along the conveying pipe. For the electricity records, it is very important to know the pumping electricity for different water resources, because the conversion factor of deep water is only half of the conversion factor of the shallow water, the shallow wells. So the corresponding conversion factors must be used to convert the fraction of electricity for the specific water resources. But usually in history, there is only total pumping electricity available. What we do to solve this problem is we estimate surface water use from water imported. This data is given by the Water Resources Bulletins. And we convert this amount of surface water use to electricity and deduct this electricity from the total pumping electricity. Now what we have is the total electricity for pumping shallow water and deep water. But there are two unknowns in this equation. So we introduce one parameter, a C value, which is the ratio of deep water use and shallow water use. These parameters can be estimated from the irrigation areas of the deep water and the shallow water. By introducing this parameter, we could calculate the pumping volume of shallow aquifers using this equation. This parameter is very important. I will still mention it in the following slides. Now, we have got the abstraction of a shallow aquifer based on the electricity consumption. Now we look at the recharge. First, the seepage from surface water. Some seepage comes from the river. It is at the boundary of the Guantao County. You can see the pictures below here. And we use the empirical functions from National Water Resources Assessment, which is a function of a river runoff entering the county. Using this function, we can estimate the seepage of the river yearly. There is also seepage from the canal in the middle of the county that is used to transport imported water to the whole county. You can see the picture here of the canal. We also use this empirical function from the National Water Resources Assessment, It is a function of the total water imported, and the parameters needed is the water use coefficient and seepage coefficient. Because the upstream also needs water to irrigate, so the water imported to Guantao usually comes sometimes comes to Guantao in the non-pumping irrigation season. So the usage coefficient is low, only 50%. Now we get the seepage from the surface water bodies. Let's look at the recharge from rainfall infiltration and irrigation backflow. Because the infiltration from rainfall and irrigation backflow is very similar in mechanism, so we look at them together. The most straightforward way to estimate infiltration is to use the function of that apply an infiltration coefficient to the total water that applied over the ground surface. There is two questions needs to be solved to estimate the infiltration coefficient. First is the infiltration lag. That is after how long time the water will reach the groundwater surface. The second is whether this water flux and reaching groundwater surface, groundwater table is flattened or not. Do we need to take into the seasonality of rainfall into account to calculate the infiltration amount rate within a year? So these two questions can be solved by simulating unsaturated zone using Hydros 1D. The previous research on the whole Hebei plan show that the infiltration amount is influenced by the total amount of rainfall and irrigation water. And the lag and flattening of flux is influenced by the depth of groundwater table and the lithiology of the soil zone. We also did the similar simulation using Hydros 1D in Guantao, and more details will be introduced by Dr. Lining later. And in simple word, in Guantao, the depth to groundwater table is larger than 20 meters. So the water entering groundwater table is flattened over time. And it usually takes about 5 years that the water enter the groundwater table, which means when estimate the infiltration of 1 year, we can take the average of the infiltration water over the last 5 years. And to determine the value of infiltration rate coefficient, we can look at the period between 2 years with the same water level in history. In this period, since the water level in the 2 years at the beginning and at the end of the period is the same, which means the change of the storage of the aquifer is equal to 0. Then the discharge equals to recharge. Now let's look at the water balance equation. Now during this period, the change in storage on the right side of the equation equals to 0. And we have already got the estimation of abstraction from electricity. We also calculate seepage from the empirical function. And we know the annual rainfall and annual irrigation water. The only unknown in this equation is the infiltration coefficient beta. Then we can calculate the infiltration coefficient of Guantao County. It is 0.17. And with this parameter, we can calibrate our model against the observed water level to get the value of a specific yield, which is 0.043 in Guantao County. We also did the parameter sensitive analysis. We compared the parameters of the error in electricity data, rainfall data, error in water level, seepage, and also the parameters that is used to estimate the conversion factor in history. Also the C values that we introduced to identify the fraction of deep water and shallow water. You can see that the C value is the most sensitive, contributes the most uncertainty to this model. And the parameters related to electricity to water conversion, the magnitude is similar or comparable with the error introduced in rainfall data measurements. So we keep the uncertainty from the C value in the following analysis of the box model results. Now let's look at the homogenization of the box model. Because the box model look at the object as a whole, we only calculate the box model at a yearly step. For recharge, as introduced in previous slide, the water flux entering groundwater table is flattened, and we taking the average of last 5 years to calculate the infiltration of this year. So it is no problem that we do it at the yearly step. For seepage, because the seepage water reaches the groundwater in the same year, so as long as we know the total water seepage of 1 year, we can just calculate it. For pumping, it is similar. The pumping happens with immediate effect and also within the same year. So whether the pumping happens at the beginning of the year or at the end of the year, it doesn't influence the water balance analysis. As long as we know the total water volume pumped in a year, we can do the calculation. The box model also neglects the spatial variability of the variables. We get the groundwater pumping from electricity consumption, and we use the total pumping electricity. So the covariance between the electricity use and the spread in conversion factors in spatial can have and contribute some uncertainty. And we did the test that the error in this upscaling is less than 5%. That means the difference between the calculation at the county level and the conversion at the village or district level is less than 5%. For water level, we use the average of 3 long-term monitoring wells located in the north, the middle, and southern part of Guantao County. By comparing with other short-term monitoring wells, these 3 points can get a representative mean value of groundwater level over Guantao. So, which means the neglecting in spatial and temporal variability of the box model is reasonable, is acceptable. So, this is the model inputs. For abstraction, we use the pumping electricity to estimate this abstraction. In history, usually only the total agricultural electricity consumption is available, and before 2007, there is only rural electricity consumption, includes not only agriculture electricity consumption for pumping, but also the electricity use of domestic and other use. So we need to pre-process this rural electricity consumption, which I will introduce in the application part of my presentation. We also need rainfall, annual rainfall to calculate rainfall infiltration. The data can be obtained from the Water Resources Bulletin. We also need the imported surface water to estimate the irrigation water that come from surface water, and also to calculate the seepage from the canal. River runoff is also needed. The annual values are needed. The water levels from the 3 long-term monitoring boreholes are used to calculate the mean groundwater level in Guantao County. The water level can also be obtained from the assessment report. So this is the model outputs. We can clearly see the yearly recharge components. Most of the recharge comes from the rainfall infiltration, which takes more than half of the total recharge. And about 20% of the total recharge is irrigation backflow, these purple bars. River seepage takes a small fraction of the total recharge, as well as the canal seepage. The seepage from the canal was very little in history, but since 2014, a large amount of surface water is imported to Guantao. So the seepage from the canals also increased in the recent years. Now, after looking at the recharge, we can calculate the water levels yearly. The black line is the observed water level over time, and the gray dashed lines, 2 lines, is the calculated water level from the box model. There is an uncertainty band because we only have the total pumping electricity in history. So we need to introduce this C value of ratio of deep water and surface water use to identify this water from this deep and shallow aquifers. So there is an uncertainty band. You see, for the years from 2017, we have a better electricity data. So we have a determined calculated water level without the uncertainty band. If we look at back into history, for the year after 2000, the observed water level is more close to the line that use the C value as 0.3. This is reasonable because in recent years there is a deep groundwater used. Many places of deep groundwater used, and it is also close to our estimation of according to the irrigation areas of this deep water use. And if we look at the years before 2000, the observed water level is more close to the calculated line that assume the C equals to 0, which means there is no deep water use. It can be, there is the other possibility of this close to the C equals to 0 line, because in history, there is still some water some diesel pump used before 1990s. So if we only estimate groundwater abstraction using electricity, there can be some underestimation that leads to the underestimation in pumping and thus overestimation in water level. So after analyze this fitting to observation, we can also look at the source of uncertainty. The source we introduced in the previous slide is the uncertainty in C value, which is the ratio of deep water and shallow water. We also compared the uncertainty from the conversion factor that is calculated using the equation to determine the historical conversion factor. We just assume it is the error is 20%. We can see that in most of the years, the majority of the uncertainty comes from the uncertainty of C values. But in extreme low water level years, which means in extreme dry years, the uncertainty from the conversion factor can be larger, because in extreme dry years, the pump efficiency could be decreased dramatically due to the decline of water level. So now we have already set up the box model in Guantao shallow aquifer. What it can be used to solve what kind of problems, and it can be solved. It can be used to simulate the water level of a groundwater table in the shallow aquifer as a substitute option of a distributed numerical model. It can also analyze the water balance. I will introduce one by one. First, let's look at the water level simulation. Taking the example of a dry year, the year of 2017. We can give the estimation of abstraction based on the pumping electricity, and given rainfall and irrigation waters and surface water runoff and imported water. We can calculate the recharge, then calculate the change in storage and get the calculated change in water level. Compared to the observed value, it is quite close and the accuracy is acceptable. So this model, this year can be used as a typical year for the dry year, for a typical dry year to analysis in the future. For example, we can analyze if we decrease the abstraction for irrigation, how the water level will change. And we can also do the calculation in the other direction, saying that we have a goal that the groundwater level in the shallow aquifer should not decrease by 0.1 meters. And to reach this goal, how much abstraction can be taken at maximum, then we can calculate this. So using box model, we can do the scenario analysis. The changes in storage can also be calculated to look at the gap, which is the difference in recharge and water use that is abstracted from the aquifers. Look at the period from 2007 to 2019, when we have the relatively good quality of pumping electricity data. We can see that the change in storage of a shallow aquifer is only around close to 2 million per year, and the change of water level per year is only less than 0.1 meters. So the overpumping in shallow aquifer is not significant. But if we look at the deep aquifer, because there is no local recharge to the deep confined aquifer, the overpumping of deep aquifer is still a lot, and the gap in groundwater use is close to 30 million cubic meters per year. And the box model can also be used to analyze the change in recharge and discharge components of the aquifer. We can answer one question. It is that looking at the water level in history, since 2000, the groundwater level in shallow aquifers did not decrease that fast as before 2000. What is the reason? And we can compare the period before 2000, after 2000, and this is the result. You can see that the shallow water use is decreased by 5%, and at the same time, the total recharge increase. The total recharge increase because the rainfall infiltration increase because there is rainfall, more rainfall, and also the deep water use and surface water use increase, which increase the irrigation backflow, and it also contributes to the total increase of recharge. And at the same time, the river seepage is has a little bit decrease, but canal seepage from the canal is increased. This is because since 2014, there is more than 30 million cubic meters of water, of surface water imported to Guantao. So there is more surface water available after 2000. That is why there is increase in canal seepage and also surface water use. And at the same time, the deep water use also increase. Here comes one question. The rainfall increase, the total water use should decrease because they do not need to irrigate in wet years. Why the deep groundwater use also still increase? That is probably due to the increase of greenhouses that plant vegetables in Guantao in the deep water use areas. And the other possibility is that in history before 2000, there is still diesel pumps used before 1990s, so the estimation of abstraction can be underestimated for the years before 1990s, and that amount of water underestimation is mostly contributed to the deep water use. So a box model can help us answer this question, why the decline rate of water level is not so fast. That is because the groundwater use of shallow aquifer decrease, and at the same time, the rainfall increase and also the irrigation backflow recharge increase due to the increase of use in deep water and surface water. Now let's see whether this box model can be applied in the whole North China Plan. The areas should satisfying the following conditions. The depth to groundwater table should be large enough to exclude phreatic evapotranspiration, and the exfiltration to surface water bodies should also be negligible. Compared to the vertical exchange, the lateral flux and can be ignored, and exchanges with the deep aquifer can also be ignored. And the irrigation water is mostly pumped by electric motored pumps, so we can estimate the groundwater abstraction using electricity. We did the outscaling first analysis in 7 counties next to Guantao counties, and the data we have is from Water Resources Bulletin and rural electricity consumption from the statistical yearbooks. Since the rural electricity consumption includes not only pumping electricity but also the non-pumping electricity, we have an assumption that the electricity consumption for non-pumping use grows smoothly with time as the economy grows. And we can assume that the randomness of annual rainfall is the cause of interannual variability of rural pumping electricity. So using this assumption, we can using the detrending method to extract the interannual fluctuations in the rural electricity and apply these fluctuations to the estimated mean pumping electricity to get the time series of pumping electricity. And you can also take into account the influence of declining water level to apply to set up the pumping electricity that with an increasing trend due to the declining in water level. So this is the result in Guantao County. Compared to the real pumping electricity. You see the trend is captured by the rural electricity consumption, but the annual fluctuations is not so obvious as the real pumping electricity data. This is because since 2000, the fraction of non-pumping electricity use is much greater than before, and the signal of pumping electricity is covered by the non-pumping electricity use. But with this in mind, let's look at the results. The calculated change of water level in the 7 counties, including Guantao, and together with Guantao County. This is the change of water level. You see the calculated, red dots generally goes with the observation. The trend is okay, but due to the missing interannual variability, and in some years, in high years and the dry in wet years and the dry years, the change is the model result is not that good. But the trend is generally okay for these 5 counties. But there are 3 counties that the trend is not good. We speculate that this is because of the uncertainty of source of water. For example, this Wang County, there is more surface water used in this county. So if we introduce this, oh, sorry, my PowerPoint is not working. So, if we take this into account, one moment. So you can see from, so this is the uncertainty band. So we are confident that given the pumping electricity with good quality, we are able to get the more accurate results from the box model. We also developed the box model in Excel. It contains the inputs and outputs are very straightforward and can be easily transferred. The data you need to put is in the water level and electricity data and the rainfall and surface water information. I can explain it in this Excel. Now you look at the Excel version of the box model. This is the 1 year box. It is the first function of this model. And this 1 year box gives the simulation of a water level of 1 year. If you put the depth of groundwater of the previous year, the pumping electricity for different water resources, and the average rainfall of past 5 years, and as well as the irrigation water, river runoff here, and the surface water imported here, given the parameters of Guantao County. The results is given in this table, also in this sketch, this figure. We can try if now the pumping electricity for shallow groundwater is 30. If we change it to 40, it changes automatically in this table and in this figure. You see the change in groundwater level will be more than 1 meters. This is the 1 year box model, and to calibrate the parameters, we always need to look at the historical data. Now you need the historical multi-year model. The input is in this input tab, and all these inputs are similar with the 1 year model. The only one difference is you also need to give the depth to shallow groundwater in irrigation seasons to estimate the conversion factor in history. For electricity for electricity data, if you only have the total pumping electricity, just enter it here. And if you have more information about from the different sources of water, you can just enter the pumping electricity for each source of water here. The parameters is entered here, and because there is only total pumping electricity in history, the C values is entered here to take into the uncertainty. If you change the parameters, this figure will change correspondingly for you to calibrate. For example, we change the infiltration coefficient to 0.2. Then the figures, the calculated water levels also change in water levels also changes. And if we change the range of uncertainty of C value, for example, from 0.2 to 0.3, then the uncertainty band is decreased. And all the intermediate variables can be found in this figure. You do not need to do anything in this sheet, but you can find the variables that you need within the calculation. The figures shows the outputs of the box model, as I explained in the slides. Also the recharge components of the box model. There is also a parameter lookup table for the users to select the possible parameter values. These values are given by the local water resources assessment report. So coming back to our slides, The box model developed for water balance analysis of a shallow aquifer. It has a very simple structure and good availability. All this data, except for electricity, pumping electricity data, you can get all the data from the local Water Resources Bulletin. And if you don't have the pumping electricity data, rural electricity data can also be used to give you a general idea. And because we have the reliable groundwater abstraction estimates from pumping electricity, we could better determine the parameters, especially the infiltration coefficient parameters, which is very sensitive for a water balance model. And this box model can be used as a simplified method for decision support. So this is my presentation. I would like to thank you for your time.